answers to these two questions. What did the largest conventional oil field ever discovered in the North American basin and the first world-class oil field ever discovered in Deepwater Classics deposit in the Gulf of Mexico Basin Complex have in common? They're found in carbonate bioclastic reservoirs. The first Deepwater Classic field was Poza Rica field. It'll ultimately produce about 1.5 to 2 billion barrels of oil in its shallow depths, relatively shallow. And the largest conventional oil field is Canarell field. Canarell in the Sahel complex will produce about 13 to 14 billion barrels. What is the name of the first world-class giant oil and gas field discovered on the North American continent? And what reservoir is it pooled? That would be the Lima, Indiana field. It was found in 1884. It started out actually in Ohio and expanded into Indiana by 1886. Ultimate reserves on that are about half a billion barrels of oil, and that's what it takes to make a world-class giant field. Okay, I started looking at the Smackover that's been about 4 or 5 Thanksgivings ago, and I was trying to figure out where you make an oil play in the Gulf of Mexico. I felt that the Permian Basin was had too many people already in it, and a lot of the acreage there had gone back for 50 years. Tough to get in that place. I looked at the Smackover, and the reason why, I figured the Smackover, you didn't have to worry about source. Source is right at the base of the Smackover. Moved right up section to the Smackover oolites. Also, I realized there was a lot of stratigraphic irregularities in the Smackover. I started looking at it a little closer, and I realized the biggest field in the Smackover trend is J field. It's a flank field. The top of the structure is actually barren production on Smackover. It actually produces from Norphlet sandstones. We start out here with a paleogeographic maps, early Triassic, the opening of the Atlantic. By Middle Jurassic, you're just starting to get the Luan salt deposition there. Actually, late Middle Jurassic, 170 million years ago. You come down to late Jurassic. This is UJ2 time, which would be the Reynolds. And that's what things look like back at that point in time. This would be probably the kind of Kinetic Diagram right there. Today it looks like this. Maybe we're going to do this, it's easier. Oh, that's working now. Okay, this is the Oxfordian Smackover Paleogeography. This comes out of GSA Geology North America, Volume J. And what we see is a series of greenstone shoals that ring the Gulf of Mexico Basin. With Smackover deltaics here, these run down the old ancestral Mississippi embayment river valley. Down here, Sabinas Basin, South Texas, East Texas, Kinetic embayment in the area over there. Down here in Guatemala, you're still in Todos Santos time, where it's be Cineris Classics there. Basic strat chart, and this just mainly I'm showing this strat chart because it shows pretty much all the way through the middle to late Mesozoic. And what we see here is mainly 4 source rocks. Most of the oil and gas in the Gulf of Mexico rift basins landward of the lower Cretaceous shelf margin, Van, Hawkins, J formation fields, these are sourced by the Oxfordian Smackover. It's a major source rock in that area. And by the way, these are not in Smackover carbonates. Those are in Woodbine sandstones mainly. That's a world-class giant. That's a world-class giant oil field. Most of the greatest source you have within the Gulf of Mexico Basin is the Tithonian Bossier Shale. They don't call it them. They call it Pimienta Shale down there in Mexico. That's what sourced Canarell, Thunder Horse, all the Great White, all these Wilcox fields, as well as Poza Rica and the Golden Lane. So this is by far the best one. When you get to this source rock, field size changed by an order of magnitude. That's where you get in these billion-barrel fields in the deep water. Then you come up to an Aptian source here, and of course we all know about the Turonian source, which sourced the East Texas field. Go the wrong way. There we go. I'll go over this slide very quickly. This is a basic slide that shows what I would be talking about here, everything from the Norphlet all the way up through the Buckner. The reason I'm showing this slide is there's our source rock there. There's our main reservoir here. Ordinarily, most of the oil goes up because you source below and it goes right up to section to the grainstone reservoirs if they exist. But there's no grain storage reservoirs there, or any kind of porosity and permeability within the upper Smackover. The source moves down into the North Lip. That's what you see in J Field. That's why J Field is barren on top of the Smackover, but loads up into the North Lip. It's the main focus area of this talk. We'll really be right in here. We'll talk a little bit about this, but not a whole lot. You can kind of see the reason why. Most people are making the oil play up in here. You got some gas plays around the northern part of these salt basins here. But really, it's too deep and hot down through here for the most part to make a good Smackover play. And you get a lot of thermochemical sulfate reduction in areas like the Wiggins Uplift, and over here I probably have it there too. Down here you may have it. I know it's very hot there, especially since you're in the Rio Grande Rift, which has been active in a tertiary. This play up in here, I think there's probably a play to smack over there, but only a few wells have been drilled, but they tend to be deep. So this gives a schematic diagram of Smackover weather system. And what you're dealing with is winds that came up, Chinook winds, came up, rain all fell as a rain shadow effect on the backside of the Ouachitas, and then dry air came down to the Gulf Coast area, which there's your Smackover Buckner carbon evaporite system there. This is another slide. It shows the ramp sequence we have, UJ2 transgression, which is a Reynolds transgression in the high stand track. A ramp series here, and then it's switched over at by the time you had UJ3 or Smackover B time, develop a little bit of a reef margin here, or at least a barrier at the shelf margin. You started getting mullite stacking up through there. So you go from ramp to rimmed, and that changed everything. That's why you have the Buckner anhydroids come in. We'll talk about all these fields with the exception to Oaks. I had to cut my slideshow back because I didn't want to make it too long. But what you see here, basically, these are all high-energy carbons down through within the Smackover. We'll talk about Midway, which is a Reynolds producer, also has produced it out of the Bond Zone, in my opinion. The Mount Vernon Field, Walker Creek, Charlie Beach Springs here, and Corny Bayou. That's structural stratigraphic, structural stratigraphic, structural stratigraphic, structural stratigraphic, stratigraphic. What this slide tells you is there's a lot of stratigraphic oil and gas in the Smackover, and a lot still remains too. What's the basics of the petroleum system? The hydrocarbon source rocks, the lower Smackover line mudstones. They're type 1 kerogen or oil prone. The seals are mainly the Buckner anhydrites, but you get some inter Smackover low energy limestone seals, and Buckner shales can also be local reservoir seals in some up-dip areas. In fact, in the Reynolds, a lot of times that's what your main seal is. You get support maybe from the anhydrites, but that's your main seal. We'll see that as we go through. Reservoirs mainly oolites deposited during Smackover C, B, and A, or A is actually lower Buckner. High stand track cycles, but Smackover pelloids, microbialite reefs, and sandstone can also be important reservoirs. Hydrocarbon traps, mainly structural, example given, Magnolia Field. And structural stratigraphic, biggest Gambit Creek, oilfield complex, the biggest one in the trend. It ultimately produced about 2 TCF of gas and 500 million barrels of liquids. However, some traps are almost entirely stratigraphic. That's Little Cedar Creek. These are just now being looked at very heavily. Charge time in its upper Cretaceous for the oil and through the Cenozoic, which is gas. Main hydrocarbon producing areas, East Texas Basin, Arklatex area, Mississippi Salt Basin, and Connecticut Embayment. Future hydrocarbon producing areas are South Texas, Florida offshore, San Marcos Arch Plunge, and Mexican Basin complex, including the Sabinas Basin, which has had some wells drilled into it, and they've actually kept some gas out of the Smackover. This is basically a electrophases log through the Smackover and the surrounding section. What you see here is a SP on the left, a deep induction on the right. Start out with Eagle Mills, which is your late Rift Valley sediments. Werner hydrite, which forms the base of the salt. Northwood sand, which is a producing unit. Then you go into the lower Smackover line mudstones, which is the main source rock in the sequence. Middle Smackover, packstones, and waxstones. And finally get in the upper Smackover A, B, and C oolites, sealed mainly by the lower Buckner anhydrite shale seals. Also, you get seepage reflux from the anhydrites down here that tends to give you some dolomization within the upper Smackover. Ultimately, the system sealed by this, but what is leaked through, especially where there's no anhydrites, sealed by the red shales, usually. Over here, again, talk about the main source rocks in the Gulf of Mexico Basin complex. We'll focus on the lower Smackover mudstones here. You'll notice this one, it actually starts, it goes from 50 to 60. They've broken the chart. This one goes out to 83, which would be over here. It's off scale. That's why you're getting all these deep water fields. You get gas and some oil sourced out of your Eocene rocks. Deposition of the lower Smackover lime mudstones. What you have here is stretched continental basin here. This would be this Angelina Caldwell flexure here. Yeah, and mainly what you're looking at here are these aborted rift basins you have in back of the Angelina Caldwell flexure and in back of the Sligo margin. You also have Smackover evidence for Smackover down in here. But what's sourced most of these interior basins is the Smackover. Even in the East Texas field, which has 6 billion barrels out of the Eagle Ford shales, sourced by the Eagle Ford shales, it's not coming from the well, East Texas is coming from the Eagle Ford shales, but most of the rest of production on the northwest flank of the basin comes from the Smackover equivalents. This gives you an idea where the source rock was deposited. That's the limits of the late Jurassic hydrocarbon source rock deposition. This comes out of USGS. I thank them for the map. Modern day water depths greater than 660 feet down in here. Get an idea of what's going on. Now we go into South Texas. Work our way from South Texas to the northeast. If you look at this, Smackover oil was generated from about 117 million years ago to 103 million years ago. That's a long time ago. And generated gas from 52 to 41 million years ago. So you got a problem there with timely formation of your traps, unless you go to a very old stratigraphic trap that had a very good seal. You come over here, and of course that's that well right there. I say it's too hot. It's too hot for most people to want to play. Similar here, down in here, where it's too hot or not, I'm not sure. In fact, I kind of consider there still is play here. Down here it becomes problematical again, in that you get into the area where you have all these volcanics and late heating. You got a problem there. This goes to this mainly. What you see is the Smackover oil was generated pretty close to the end of the early Cretaceous. Smackover gas is pretty much in the Eocene. So therein lies the problem with this area in here. You move the east a little bit. Now we're in the coastal zones of East Texas, Louisiana, Mississippi, and Alabama. And this is from work, I believe, by Lewin et al. In 2002. There's your basic basins and uplifts there. Down here, you can get an idea of what's going on with transformation ratios. Once you get to the blue, 99% of the oil has been generated. When you get to the gas, 99% has been generated. So if you're making a play, it's going to be gas down here, maybe oil up along in here, and some oil and gas in that zone right there. And over here's a chart that basically explains what's going on. You'll notice that basically you're going from oil to gas as you pass through there. This being the start of oil generation Smackover. The end is right here. You'll notice these two charts stagger, so it actually forms a bell curve. And then by the time you get over here, you're pretty much in gas. I'll put this in for overpressures. This is the only map I could find on overpressures in the Smackover. You notice the overpressures tend to follow some basement shears in a rough sense, which is part of the old Gulf of Mexico opening. But that would be the areas where it's overpressured. When you get this deep and that overpressure in the Smackover Formation, you get thermochemical sulfite reduction, which really pretty well eliminates the economics for your play. This is the graph showing original pressures versus depths in the Arkansas Smackover oil pools. And what you see, everything follows a linear trend on the earliest fields, but the later fields, the ones that were being drained partially by these, or at least the pressures were being reduced by them, you see these sitting out right in here, especially Clara field. Evidence for thermochemical sulfite reduction within the upper Jurassic reservoirs. Got two wells here, the Phillips Josephine, the Conoco Higgins wells, Josephine, the Higgins right in there. That's burnable gas. That's H2S pretty much. That's pretty much, I believe, N2 there. Some CO2, that's burnable gas. So you've got a problem when you get that thermochemical sulfite reduction. What you're producing is mainly bad stuff. And this tells you basically how things happen there. You get the reservoirs are preferentially destroyed by a reaction with metal ions to form sulfide minerals and underlying Northlet, actually in the Smackover. You get down to the Northlet, it's a little bit different situation. Smackover, it's bad news to go deep. In a way, that's good. It keeps you from drilling 16,000, 17,000 foot wells. This is a location map for the Townsville gas field. We'll be talking about this zone right here. We'll specifically be talking about the Jackson Dome. Now, if you were here in May, I basically gave you the same slide. This is a laramide volcano. And when it subsided in Paleogene time, you formed a reef over the top of it. That's the basal tertiary conformity of that. Actually, some restriction in the lower Paleocene. Here's what the volcano. This volcano sits here. Townsville field sits right in here. These fields are mainly CO2. They're using that CO2 now basically to gas lift oil out of nearby fields. There's our CO2 oil source. We'll be looking specifically at Pease Guy anticline in here. Shell was, I think, the first company to really find these CO2 reservoirs. Here's what it looks like in the cross-section. The Jackson Dome came up. And anytime you have a carbon that's got any kind of decent porosity or permeability, the igneous intrusion comes up, it just downloads all the CO2 and the bad stuff it can into those reservoirs. And that's what's happened in here. The Norfolk has some gas, as well as the Buckner Smackover and the Buckner. But you notice they say it's thermal alteration of carbonates release CO2. I think that's part of it. A lot of it just get a lot of CO2 out of that igneous intrusion. This overcomplicated diagram, and I tend to do this, and I try to put everything on one slide, but basically you see what's going on here. You got several cycles. You got UJ1, which is the original transgression of the Gulf Coast. Luan salt was deposited. You had a regression, Norfolk erg deposits were deposited then. And you come back and you transgressed again, with the main oil source of Smackover being the lime mudstones. And then you got Smackover C, B, and A through here, A being actually Buckner and age. So those correspond to UJ2, UJ3, UJ4. This comes out of Moore's designation, which I think is actually a pretty good one. I think there's evidence of wrenching here in the Buckner regression, and I think you see some uplifts. That's why the state line high was uplifted during Buckner time, early Buckner time. A lot of faults heal off right in here, so that's important to know. This is the carbonate petroleum systems. Again, this comes out of Moore. A lot of my slides are other people's slides. They've done it all for me, and I'd be glad to use their slides. Porosity types here, ulamoldic here, ulamoldic here. Ulamoldic, as you know, is problematic unless you get a lot of fracturing in your reservoir, because you'll drill a well with 22 to 25% porosity and not get any hydrocarbons out of it because it's all disconnected porosity. So you'd rather go with dolomite secondary and intergranular primary. And basically what you see is East Texas is kind of okay, shelf margin is okay. Arkansas, you have to kind of worry about this, especially when you get up dip. Intergranular porosity, primary porosity in Louisiana. Reservoir sequences, you got UJ2, which is Smackover C or Reynolds. UJ4, which is Smackover, is actually Buckner A, but I know from what I've seen, it looks like he has to Smackover B. In Arkansas, you got UJ2, which is Reynolds, some Smackover C, and some even that's a Smackover B, and some B, which is Smackover B. Okay, Buckner A in Louisiana with some I call it Smackner. There's what I call the Smackover, which is the Reynolds. Then there's the one in between the Buckner, which the A, of course, is the Buckner. So the one in between I often call Smackner, just because it's not really Buckner and not really Smackover. That's just my terminology. Don't dwell on it. Smackover carbonate diagenesis. What we see is two times here, time 1 and time 2. This is when you have reflux dolomitization, and you have the Buckner anhydrides deposited. It goes down into the Smackover carbonates below, magnesium-rich waters, and tends to dolomitize the Smackover carbonates in the areas where the Buckner anhydrides produces it. And ordinarily, in many cases, when you get past this point, what you get is pretty much crappy reservoir. So people look to where the Buckner anhydride is, and they make that play from there all the way to there. Time 2, down here you got mixing zone dolomitization, and somebody's showing, I believe it's Mr. Mancini showing freshwater infiltration, and you get a mixing zone dolomitization right in here. And I question that. Does dolomitization shown in time 2 mainly occur in areas where Smackover carbonates have not been regressed by Buckner anhydrides? This is a Walker Creek field. Somebody's giving an example on this. This is actually Becker and Moore, and they're showing freshwater phreatic zone here, Vados water table in here, and maybe that's what you're getting there. When I started all this, I said, what's really going on at Smackover? These are questions I asked myself. Anybody who's ever worked at Smackover has probably asked these same questions, or should have. There are 3 question sets. What are the main factors that determine EUR of Smackover lower Buckner hydrocarbon fields? And really, I consider the lower Buckner almost part of the Smackover. Why does the Smackover oil field? Why doesn't a Smackover oil contain a large? Why does Smackover oil field, the Smackover oil field, contain a large Smackover Formation hydrocarbon accumulation? Well, we'll see that as we go through. One of the big problems is you just don't have a good vertical seal. Why no large Smackover lower Buckner hydrocarbons in fields have been found in the Wiggins uplift? It's too deep. Too deep. Got problems with the reservoir. Got a lot of CO2 and other stuff in there. Just a bad place to be looking for money. If you want to find gas, you find a lot of CO2. Maybe it's made to us. Why does the J Formation Biggest Standard Creek field complex contain such large EURs? Because everything comes together in that field perfectly. Is reservoir depth an issue with regards to Smackover Buckner exploration economics? Yes, it is. When you get below about 15.5, you start having, especially where the Buckner has been deposited, you get problems with thermochemical sulfate reductions. How important are Smackover lower Buckner time stratigraphic facial relationships? And the questions I have here are, how do hydrocarbon stratigraphic entrapment trends relate to major Gulf of Mexico transgressive regressive boundaries? They relate very well. What you see is up-dip facies change traps, Walker Creek being one of them. In a way, you can almost say J field, another one. So they relate very well. What percentage of Smackover fields have a significant stratigraphic component? At least 2/3. What that tells you is probably a lot more left if you can figure it out. Is superposition of Buckner and hydrites critical for dolomization and vertical trap sealage? It helps a lot. I don't know that it's critical. I think when you deal with the down dip areas where carbonates keep growing all the way through Buckner into the Gilmer and even beyond, then it becomes quite a problem because you just don't have a good enough shale seal. What areas have the lowest risk and highest potential for Smackover Buckner hydrocarbon exploration? To date, most of the Smackover and lower Buckner fields have been found between the northwest margin of the East Texas Basin and the northwest margin of Florida. Very little's been, a few wells have been drilled in the plunge of the San Marcos Arch. A few wells have been drilled in South Texas. Some have been drilled in Sabinas Basin, but they have reservoir problems there. That's also gets involved in thrusting there. Do large undiscovered Smackover Buckner hydrocarbon fields exist in these picked over areas? Well, yeah. You keep finding them. Little Cedar Creek's one. What is the Smackover lower Buckner hydrocarbon potential of the southwest Florida margin? It's probably pretty good. Just the question is how far out of the shelf you have to go to get it. Does significant hydrocarbon potential exist elsewhere in the Gulf of Mexico complex? For example, down the flanks of San Marcos Arch. It does, but you have to worry about temperature and pressure. Within the Rio Grande Rift, same problem. In the Mexican basins, including the Sabinas Basin. Mexican basin has not really been played for Smackover. At one point in time, Exxon went down there and tried to cut a deal with Mexicans on doing Smackover play. But you know the Mexicans, in the end, they didn't really, they milked Exxon for what they knew about it, but never cut a deal with Exxon, which is typical. This is the regional context of J-field complex in northwestern Florida. And the thing to know about this is where J-field sits. And most of your production in the Smackover occurs in these wide profiled margins here. We get a lot of grainstones and packstones. And just what happens is the oolites just prograde a long way, and you have several cycles within those oolites, and they all tend to have their own seals at the top of the reservoirs. So it's good to have the wide profile. You get some significant production out of here. Curryfield sits in here. But the problem with these narrow profiled oolite margins is all the reservoirs stack vertically. They have grades such that you've got limestone on top of limestone on top of limestone. Problem is you don't develop a good vertical seal unless the carbonates themselves seal. When you start structuring the carbonates, it creates a problem because then you open up migration pathways. This J Formation Biggest Standard Creek is a major structural stratigraphic trap that has diagetic complication. Its stratigraphic aspects cause it to have a pressure depletion reservoir drive, which means you have to inject into the reservoir, which caused water injection to be initiated soon after each field in the complex was completed. It's also sitting dead center in the Kinetic Diagram, which is one of the richest areas for Smackover source rock deposition for as far as organic carbon. We're going to switch over real quick. I'll talk a little bit about Smackover sands. Most people know that there actually are some production out of Smackover sands, although it's not all that great. It's produced, this field here, it's got 12 wells and it's only produced about 590,000 barrels of condensate and about 8 BCF of gas. That's out of 12 wells, so it's kind of a stinker field. But what it's producing out of is Smackover sandstones. part of the problem with Smackover sandstone, if you get them, is when you get a lot of oolites in the surrounding area, the oolites blow back into these areas where you get the sand. And then you get the degradation of the oolites, and they form carbon cement. That's the problem with it. This is what the field looks like. It's what it really is, the Chula Lake field, Mississippi. And it looks to be a rejuvenated rift structure. You can actually see some of the faults go up a little bit higher even in the Buckner. Now you see the trap type given by this individual here. And as far as I'm concerned, you have to do fault traps and this number 4. So number 1 and 4 are basically the same thing. These are your Graben margin traps. And there's been, even in late history with Chandelou Field, they've had some discoveries here by doing detailed geological and geophysical work. Small and medium hydrocarbon fields here, medium to quite large fields here. Jay Stanley Creek being in there. Nancy Field is pretty good. Dorchett, Macedonia is not bad. Basement structures, small to large. Most of them are small. That's John W. Field that sits over here. The large Midway, which sits up in here. Midway, in many respects, looks like a wrench structure. It's also a very odd field because there's a little finger of Smackover oolites in the Remmel Formation that went up through there. But the reason why Midway is so big is you've got the bond, part of the lower Smackover appears to have, or the middle Smackover appears to have some reservoir in it, which I suspect is some kind of thrombolytic reef, similar to Little Cedar Creek field. Then you got small oil and gas fields here. I'd say anywhere from 8 to 25 million barrels, including Little Cedar Creek. But they're nice little fields. They're not that deep to find. I like this. Actually, I had another slide which basically showed it on a single well profile. But here's how the Smackover's the trap system works. What you really want, you want these back bar lunar deposits to be prevalent and sealing your trap in the up-dip direction. Once you got that, you're on structure, you're going to get an oil field. But you can also get these areas here where you get carbon slope deposits, finger up over that, and separate these different lobes out. So that's why you get these multiple lobes that tend to produce. This is the same thing, only I just shows you the different cycles. You're getting younger depositions, you come down here. You start out here, you got the Smackover sequence, Northlet. You get an early Smackner, what I call Smackner over Smackover B fan here. There's your progradational phase, Smackover B. Then you get the Smackover B shelf got exposed. This is kind of Buckner. So you started here 1, now you went to 2 here. So you expose these carbonates in here, and that's essentially what happened over the state line structure, and that's one of the reasons why it has such good processing permeability there. Then you come down to cycle 3, early UJ4 time, which would be Buckner, and all this gets sealed because you form a rim to margin down here. And notice how this is now a grading, not just prograding out. So that's important for sealing in the up-dip area. Here's what it looks like, an example of lithologic versus sequence stratigraphic cross-section. This has the actual sequence boundaries covered in. This is Reynolds here. This is UJ3, UJ2, UJ3, 4, and 5 here, which would be the Reynolds, the Smackner, and the Smackover A or the Buckner. And this is the same thing comparing Louisiana to Texas. And what you see in Louisiana is these all move this way, and you get separate seals on top of these different oolite complexes. But here in Texas, especially along the western margin where the fairway gets very narrow, everything stacks vertically. You have a problem trying to seal everything. So the systems are grading here, the margins are stacking here. Here the systems are prograding in the shingle, and that's one of the reasons why you have so much production there. We're going to go into salt-related structures, and this is the best one I could find for that. Start out with a salt ridge development, a salt pillow in here. This would be Mount Vernon, Walker Creek, Tubal Field, Stripe View, with an incipient salt pillow here. Then you go into stage 2, it would be Middle Haynesville time. And what you do, you start to develop an offset fault in there, and you have production out of this and this right now, that eventually. Then you come down over here, you got what's called drawbed structures. A better term for this would be salt separation structures, where the salt actually moved, separated this from this, and where you have a vertical seal here, you're going to get production here, also down in here. Remember, you're sealing against salt there. So really the question is what kind of vertical seal you have here. And then finally you end up down here. This is the incipient salt doming stage, and this is a later salt doming stage right here. Okay, now this gives you an idea of what's going on, what's been happening in the mid-90s to, I guess, the mid-2005s. Is you're playing this area in here in Mississippi, the salt wall plays. There's the logs over here, for example, what Smackover looks like. Here you got a series of fields. I'm going to show you North Clara Field, which is this field right here. North Clara Field Again, remember I said it's a three-way closure against the salt. There's a Smackover, comes through there, seals against the salt. It's right there. Simple down-thrown closure. With salt involved, you can enhance that trap. The lateral sealing capability, it'll work. This is the Architect's hydrocarbon production trends in the Smackover and Lower Buckner. This is an old basement high here, and you get a lot of inerts on this high here. I mean, very high inerts. And some H2S, I think, some of the fields, but mostly inerts. And then you've got each one of these is a different sequence. That's Smackover C, Smackover B, Smackover B and A, and then Smackover A. You see the system, how it's basically prorated time in this direction. And each one of these areas, you develop oil and gas fields. There's my state line high. You don't get any production on state line high because everything's been removed. It got, during the uplift in Buckner time, it stripped a lot of the reservoirs. This is my diagram here. I made this because in order to understand, I've got to be able to draw a strat chart. If I can't draw a strat chart, I don't really understand it. Consequently, I do the strat chart. And what you see here is you got state line highs, an old central roof accommodation zone horse. Over here, Eagle Mill's graben. Another Eagle Mill's graben over in here. This got uplifted right before Buckner time, and that's why you're developing all these fields in here. You get a lot of porosity permeability in sandstone. You'll notice I show up dip production here in each one of these. There's at least three fairways, 1, 2, 3 that I know, probably 4. Actually 4, count that one there. These two are Reynolds 1, Reynolds 2. And then on the areas where you have big salt structures, you also get production on salt structures. And you get some production out of these deep water sandstones that happen during the low stand track. And of course your Haynesville shales sit out here. Jones sand, on this particular field, we'll look at this as Schuler. Schuler, you have a problem in the late Smackover, which would be Smackover Reynolds, very tight 15 to 25 foot limestone unit got eroded there in the southeastern part of that field. We'll see that coming up. Here again, this gives you an idea what state line structure does. You started over here with UJ2 or Reynolds. And then you had early Smackover B. You see everything got eroded here. See how this has been thinned also. Now you've also, since it's a regression, you develop C-sand out in here. Then you come from here to here, and you got the UJ3 Smackover through here. There's my Smackover B, there's my Smackover C. For a long time, people thought this was this. They just figured it all got eroded. But these are actually two different cycles. That's C and that's B. It's a different cycle. And here's how it kind of works out with more wells. This is how it works. No production zone right here because the oolites are all gone. Here you have the lower Smackover brown vents. That's your main source. Here you have the Reynolds oolite member through here, and you get production all through these fields in here. Some on salt incline, some on stratigraphic traps. And then over here, this limestone, it looks like it's the other piece of that. That's different. That's Smackover B member over here. Because after that uplift, you started the prograde from a new high, which is this one here. Then you get the Buckner shales come in, and then you get Buckner A member sits right in there. Okay, now we're getting to where I really wanted to be, which is what are the rules for finding the big field? Everybody wants to find a big field. Nobody wants to find a little 2 to 15,000 barrel field. Right now it's good, but bad times that's not good enough. So rule number 1, you got to be in an area where Smackover reservoir facies exist, and one or more of these facies cover most, if not all, the hydrocarbon trap. Best example for that is J field. In fact, the best example for almost all these rules is J field. Why is J field so big? Look at the back reef lagoonal facies that comes through here. They show this as isolated. I'm not sure it's totally isolated, but that's the high point on that facies right there. By the way, that's formation is covered by these back reef oolites, or back reef low energy carbons right there. That's why J doesn't produce, or the top of the structure sits actually right here. That's why you produce out of the Northwood. It's loaded down into the Northwood because it couldn't go into the Smackover. Biggest Scammy Creek sits here, Black Creek sits over here. So we're backed by back bar lagoonal carbonates. We're fronted by open marine foreshore carbonates sealing facies. That's why it's so big. Then you go rule 1, the same thing. The updip shelf fields, which are these fields right in here, hinge line trend. That's decent sized fields here. That's a relatively big field for the Smackover. And some big fields down here, Curry Field. Also, you want to have the right reservoir facies over one or more. Must cover most, if not all, the trap. In this case, There's my state line high down through here. I've got a series of Smackover oolites that tend to go out, that program offlap this high, but now it's sealed up dip. And actually, if you find out what it's sealed for, it's kind of a strange thing. It's actually a silty sandstone. That's what the seal is. Look at that. Would you drill that trap after you knew? If you saw that structure map, would you drill that trap? And the answer is pretty gutsy, but remember you're on a big nose where these oolites prograde, so that's a good place to look. So here's the same cross-section I showed you before. It goes into Walker Creek Field. That's the Smackover B oolitic reservoir. That's where the main producer is. And you got several oolitic reservoirs, not one. You're just in the northern part of the field. That's just a particular one. You see you've got like 4 or 5 of these oolite lobes. But look what it's sealing into. I always said, well, once the Smackover gets intermixed, the sand up dip, you're toast. You're not going to, everything will bleed off into the sand. Well, guess what? That doesn't happen. When you think about it, it's kind of obvious. If you got all these oolites down dip, and you're washing oolites back into the sandy transition zone here, that means some of these oolites are going to be retained as oolites. Some of them will actually be redissolved and form carbon cement. So you got a natural stratigraphic trove. And here's what they look like. Zone 1, the oldest bar, zone 5, the youngest bar, and the direction of progradation is this way. And this is a very big field. How do these oolite bars, what's a step over between the bars? And what you basically see, salt tends to control things. Carbonates are substrate control. Once you realize that, you're about 50% there, because you want that have an advantage to light, and you want separation, if you can all get it, between any kind of muddy waters. Carbonates don't like muddy waters. So essentially, there's a place where the salt expands down here. This oolite trend goes out, and then you come back a little bit, and then you have another one through here. You have a Buckner thin over here and a Buckner thin over there with a Buckner thick. So what's the key looking for the Buckner thick? You want to find those Buckner thicks. Seismic parameters for making the plays. Slope change to the base of salt, fall to the base of the salt, isopac thin in the Buckner, mistized seismic reflectors, porosity measurement Smackover. I'm glad to cut this one out. I had to get rid of about 30 slides just to keep it within distance here. Keep it within an hour. This 3 different fields: Kiln Creek, Walker Creek South, and Walker Creek. There's top of Smackover. Where's the structure? Hard pressed to find it. But that's it. There's the base of the bows. You notice it's unfaulted. That's somebody's interpretation of it. Okay, rule number 2: you got to have favorable diagenesis over most of the Smackover or lower Buckner, which I consider as kind of extension of the Smackover. Oil and gas trap area, allowing for early hydrocarbon pooling that could impede diagenesis in a poor stabilized oil and gas reservoir. This is Mount Vernon Field. It's EURs, it's probably already produced this now, 8 million barrels and about almost 6 BCF of gas. You can see where it is. This is out of Reynolds 2 oolite bars, what this is. Go back to my diagram. This is the second bar system in. And by the way, when you come to these reservoirs, they all kind of ring around through here. It's not just one field. It's several fields. They all follow that up dip boundary. Look at how narrow this field is. It averages about a half mile in width. We'll see 3 different logs here. We'll see what's giving us our seal here. This is from Moore and Druckmann. Actually, Moore writes a lot of good papers, and thank him for a lot of good work he did. Same map down here. Here, 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 here. So what do we see? We got one producer in this sequence. We got 1.5 mile between this well and this well, and 1.5 mile between those 2 wells. Very low perms in the Smackover throughout, but it's almost all oolite. What's between this and this? I would say it's probably a structural advantage. This is a lower part of the bar. It got cemented up. Just no good. Low perm. And I don't know if it's necessarily totally a good seal, but you don't get anything out of the field, anything out of that well. This one's got oil-charged, porous, and very permeable oolites. A few crappy perm zones in here, but all in all, this is a quite thick zone here, so you get some perm zones that actually work pretty good. You may actually even have 2 cycles here, a lower and upper cycle. Then you go to the backshore page and look at this. It's just tight as a tick. Here you got more permeability here than you do here, but not a whole lot. So that's our sealing phases. So we went from crappy reservoir, if any, good reservoir to crappy reservoir, and you've done all this in the space of 2 miles. So that tells you what the opportunities are left in this trend. This is hard to read. This is one of these do-it-all slides, okay? Don't even try to read all this because I'll interpret it for you. I know what it says, otherwise I couldn't read it myself. This is a Catnap, or what really seals in the carbonate reservoirs. You're asked why Smackover field doesn't work. Down through here, the Jones sand, Haynesville sand, comes in. You have an unconformity surface, type of Smackover. It comes in and gets poured right over these Smackover carbonates here. So there's no vertical seal. Unless the Jones sand, it doesn't have to be permeable at that point. Or even worse, it was permeable, but not at the right time when you catch the old charge. So when you get into this area up in here, you're toast. And what is that Jones sand? It's coming out of Mississippi embayments, what it is. It's part of that overall classic system you get out of that embayment. Smackover field up in here, you just retain very little Smackover oil. Now, by the way, that's what the Smackover Formation is named for. It's for that carbonate was drilled there. But I'll be surprised if you produce 2 million barrels out of that field. And it's a 500 million barrel field or more. It's a big field, but it's not in Smackover. So you look at these ones up in here, you get multiple types of seals. This area right in here, you get that very tight carbonate right at the top of Smackover. And ordinarily, I'm not excited about carbonate seals, but like Little Cedar Creek to the southeast, it works very well here. And where you have it, you get a field. Where you don't have it, you start having problems. But also, you have Buckner above it, so you get a double trapping system. You got the tight carbonate seal, and you're just covered right above by the Buckner anhydrite. Consequently, you're just getting a good seal complex. Down in here, what's sealing here are the Buckner anhydritic shales down through here. That's mostly Smackover B. Smackover B runs through here, 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 here. Smackover C runs down through here. Remember that diagram I showed you a little while ago? Rule number 3, you must have a common cap lock lateral base seal over Smackover Reservoir. We'll take a look at this field right in here. There are no Smackover producers here, but you've got a closure, structural closure 4-way, proven by the wells. There's your field up in here. Later salt movement, or is that just wrenching? I'm not sure. The reason why I'm not sure is this side's steeper than that side. It's not a thick enough dome to be overhanging to the south, I don't think, so it may actually be a wrench fault coming through it, maybe. The important thing to know is this is not productive, that is productive, and this is thin here, and that's thick there. This kind of pretty much tells a story. This is south direction cross-section, runs through here. Remember that little thin limestone I said that's in there 15 to 25 foot thick? That's what's sealing in the Reynolds gas and the oil from the Jones sand. Now you still have some gas up in here and even some oil down in here, but basically if you don't have that facings, you're toast. You have to have that separating that from that. And that line runs in there. So we'll look at the other cross line, which is the kind of the pink one. Now we see what the problem is with the southern part of the fold. It's in areas that's been totally eroded. So all the oil went up into the Jones sand, and it's producing there. Here you get some up in here. But this one seals. There's my tight limestones, my seal. Poorly developed, breached in some areas, no seal. That's why that doesn't work. Now we'll go into East Texas Basin. What's the problem with the East Texas Basin? People have worked it pretty much know. You get in this area up here, we get a Buckner anhydrite above it, or some Buckner anhydritic shales. You're okay. That's this area up in here. As soon as you step off the front of that, you're somewhere down here. What happens is, this solid limestone from there, you're hard pressed to see. You see a shale break. If you get those shale breaks, your chances of finding the field are pretty minimal, especially if you're looking for structure. Most people are playing structures. So you got a problem. We've talked about Mount Vernon. We've talked about Walker Creek. We're going to talk next about Chalybeate Springs, but keep in mind, Corny Bayou, if you extended this map, will be right about here. We'll talk about these last two fields. And Chalybeate Springs will surprise you. That's the Phelps sand. That's a quartzose sandstone. That's the base seal for my hydrocarbon trap here. Then you got an up-dip Smackover bead quartz sandstone with oolitic facing seal. That's my seal above it. That's my producing zone that sits right in there. We'll look at a cross-section that runs from here all the way down into there and then back out to here. What's it look like? Okay. There's my oolitic, this is Phelps sand, it's a quartzose sandstone. That's the base seal for this trap. Who'd have thunk it? Look at the up in here, the oolitic grainstone, that comment goes to this right in here. Notice how you're decreasing your crossing from 20% down to 10% there. That is actually quartz sandstones with oolites serving as a good seal. So here I have a situation where I have an oolite reservoir sandwiched by sandstones, yet it's still producing. The reason why is I get a lot of wash over these oolites. They seal up any kind of quartzose sandstone and give you a good seal. Here's what it looks like in cross-section form. We'll focus on this and probably go on. Reynolds 1, Reynolds 2, these are the two Reynolds members. And you'll notice this is time 1. Now you've got the Reynolds exposed there. Now you put the Phelps sand over that. Okay, there's my sand getting deposited over it. You think it'd be a thief zone for that. Now you prograde. Phelps sand is laid down. All of a sudden you prograde out a little bit farther. You lay down the Uolite bar in the smack, what I call the smacker or the middle Smackover. And there's my Phelps sand sealed. Now I'm starting to seal by red shale, but ultimately it's sealed by the classes that's coming above it, the calcareous. This is Corny Bayou. What you see here is a series of kind of reefy kind of things in Corny Bayou. This one produces. That's not. Basic reason is Jones Sand again. It's the thief zone. That one I know is texture not. This is just a schematic diagram. But it's important to know that Buckner anhydritic shales do seal. Rule number 3, you must have a competent capital base seal of the Smackover Reservoir system. The best examples are these two fields right here. This is sealed by carbonates. It's not. There's no Buckner anhydrite facies up in here. That's sealed by carbonates. Out of 2 zones, a lower and upper zone. Usually when you get a lower upper zone, you get a pretty big field, but we're very close to connect a basement ridge in here. But that's about a 25 to 35 million barrel field, and it's not that deep. Upper Uolites, lower reef. You actually had a reef grow on the transverse high in here. J oil field complexes in colloidal and oolitic shoals down through here. Again, there's my main sealing faces in here. All this, there's my sealing faces out in front. All the oil in this area came up to this high. Here's the reason why it's so big. You get a long linear salt ridge in here that acts as a focal point for everything. You get oolites coming off, you have pellets coming off here. It's important to know. This is just a closer view of the same thing. Here's Formation Field. Top of the structure really runs right through here. That's the top of the structure. Flank Production, biggest family keep. Flank Production in J Field, some in Blackjack Creek down here. That produces no oil out of Smackover. Smackover there is tight. It's sourced down into the Norfolk. But that's the top of the structure. Production's all right in here. Here's a J Field cross section. It's just one that runs right through here from J Field on down. And you come from the inner shell of actual hydrocarbon seals. You come all these dolomitized grainstones. Probably more than one cycle. Backbar lagoonal facing. That's what makes it so big right there. Solid backbar lagoonal hydrocarbon seals. That's what makes that field so big. Anytime you get that, you know what it is. You just start looking. You can find your oil field. Rule 4, you must be in an area where you have a very large, well-sealed structural or stratigraphic closure, or several oolitic lobes terminate a major Smackover and over Buckner Formation cycle boundary on the same anticlinal closure or stratroid. This includes double plunging and single plunging anticlines. So sometimes a nose is good enough. After all, that's what Walker Creek is. Or deeper basal upper Smackover microbial reef facies pervasive over the same area that contains a shallower hydrocarbon pool and younger upper Smackover oolites. That's Little Cedar Creek field. Probably it's Midway field. When you read the descriptions of Midway, it sure sounds like a thrombolytic reef. Now we come down here and we say, well, how do all these fields relate? There's a distribution of Smackover Formation oolite shoals. I've taken this man's diagram and colored in. There's J Field right there. There's Little Cedar Creek Field right there. Look at how these fields are all stacking up along the cycle boundary. Chunchilla Field sits right there. So it's important to know where these cycle boundaries end. 4A, which is a subdivision of that area with a very large well-sealed structure. That's an example of a Magnolia Field. In a way, Big Escambia Creek is one also, but it's got a stratigraphic seal. Now we get into reefs. I'm not going to cover the reefs in a big way, because that's a 30-minute talk by itself. We're going to talk about the location, Appleton, Little Cedar Creek, deep water ramp facies in here, inner ramp facies, and what you deal with a series of highs that got transgressed. And either you get fringing reefs like Location Field or Appleton Field over here, which is a transgressed basement ridge for production. 4C must be an area where deep water microbial reef facies exist, pervasive with the same area that contains a shallow Reynolds hydrocarbon pool. That's what Little Cedar Creek is. There, that's dip. Where's the closure? The closure is all stratigraphic on both horizons. Since two stacked cycles, it's important to know which cycle you're in, where the cycle's in. It's very important to know. Total Smackover ice pack, you look at this, albeit small. What you see is a little ledge in here, a little area where your contour is thin up in here on the Total Smackover ice pack. That's why you grew the reef there, and that's why you do a lot of shell bucket. So now you can see the Smackover B oolites going out. They're not in this well here. And then you can see the thrombolytic reef down here. It's not in that well either. So this well is a dry well. This shows you, I believe, Appleton, Northwest Appleton, and Burnt Corn. These are all sit on basement highs that got transgressed. So the tops of these paleo highs are a good place to explore for oil and gas. People have been doing that for the last 20 years. But also, the vacation field, look here. Smackover never made it over this high. Now I have a Phrygian reef that grew on the side. That produces all that. Also, that is a rotation field. Rule 5, you've got to be in an area where an active generation center exists, contains excellent to good lower Smackover Formation source rocks. Again, that's the showpiece for it. You're surrounded by source rock there. And everything that's being generated is going to try to go to that field. And it did. It's a big field. Rule 6, you must be in an area where the large hydrocarbon tract formed before or during lower Smackover source rocks hydrocarbon expulsion, and it was not breached by subsequent structural movements. Magnolia Field is another good example. I can think of others. There's just no faulting on that field. It's just a big salt pill that got loaded. You must be in an area where you have a large hydrocarbon tract formed before or during the main Smackover source rock oil and gas expulsion phase and never breached. There's lots of closures over here. This is the only one that works against that fault. So let's take a look at that. That's Curry Field. It's in this narrow shelf fairway down here in the Smackover. By the way, this is basic, deep basin, but not super deep. And this is carbon ramp up in here. Here's why it produces. That fault dies in the sligo. These faults aren't productive in the Smackover. You got closures, this don't work. This is the one that's open at the basin. That died early, loaded up. Got gas in actually a pretty good sized field. Rule 8, it helps to be in an area where Upper Jurassic and or early Cretaceous basement involved wrenches enhanced trap closure. Midway Field is probably a pretty example for that. That's why Midway Field, one of the reasons why it's so big. And Bryan's Mill oil and gas field. What we see over here is a series of fields stack up. Bryan's Mill here, Midway Field sits here. This is going to be Walker's Creek. That's that Shongaloo complex, Shongaloo-Haynesville complex sits right here. All these fields stack up along there. So it's important to know where these shears are. That's the South Florida shear coming up through there. There's actually another one coming through up here. I just didn't mark it. That's the South Florida shear. And it's not just the Smackover. You start going along that to the southeast, other big fields forming there. In the offshore, that's where you get your fields there, along that shear. So it's important to know where the basement shears are. Our business is one of using everything you have at your disposal to try to figure out what's going on. And explore it in densely well-populated zones. You're going to have to be able to do that. Rule 8 helps to be where you have a good wrench-involved structure. That's Midway Field. That's a good. Somebody's put a wrenching component in there. Here, what's really interesting is you've got a 6 to 8 foot thick Smackover Reynolds Italy limestone unit, but a highly porous permeable 104 foot thick zone of granular non-oolitic oil-bearing limestone called the bond zone from there to there. Doesn't that just sound like a microbial reef? It sure does. You look at that, samples of microbial reefs look just like that. That would be a middle Smackover reef. So I'm saying, hey, this is a greater version of what you have at Little Cedar Creek, because you have structural closure. Again, we're going to go into Bryan's Mill Field. I'm going to take a drink of water here before I get cut now. We're getting close to the end. The wrenching. That's typical trend for a basin, rift basin opening. But look here, this thick's been offset from this thick. That high's been offset from that high. You've got post-Austin east-west divergent wrenching that's occurred along through there. Because of that, you got Bryan's Field here, Frost Field here. In a way, you can also include that too. We'll get a cross-section right through here. Okay, well, first we'll look at the structural map and the cross-section. The cross-section will run from here to here. There's a structural map. Basically, you have dip closure here, Hard pressed to get dip closure here. It's more stratigraphic. You're getting close to the cycle boundary. Here's what looks like a cross-section. Got a field there, you got a field there. You got to dip this way, dip that way. All this is sealing in there. That's our field. You're up thrown here, but you're actually more up thrown right in there. Salt all goes out right here. Again, this is one of these hinge line province, when the basin kind of fell down, you're coming up to shallow basement here, and that's what this is right here. This author, I believe it's Harwood Moore, stated that you get some enhancing values to diagenesis because of the strike slip faulting. In other words, it's helping the reservoir. And that's one of the reasons why it's so good. So for other reasons it's good. Is that hydrothermal dolomization? I don't know. Could be. No one's making that play in the Gulf of Mexico, but it's got all the components there. Rule 9, the largest hydrocarbon fields in a basal area are going to be where everything comes together. Again, that's J field, biggest Lambda Creek. Again, you've got this big oolite colloidal bar complex right here, sealed by the back, sealed the front, fetch, everything's going for it. That's why that feels so big. So the conclusions are essentially what I've been telling you all along. You have to have a right Smackover facies has to exist. It has to be one of these or a combination of these has to cover the trap. Another area would be where you have Smackover traps going early, like for early hydrocarbon cooling that impeded Jurassic and younger bad diagenic effects. It must be an area where you have a high confidence Smackover reservoir caprock or caprocks and lateral seals over a large hydrocarbon trap. But in some of these areas, remember you're dealing with strap trap. So not only do you have to have a top seal, you've got to have a base seal too. And as I showed you before, you wouldn't think Charlie Beach Springs would have sandstones encasing that reservoir, but it does. And it would work and have a big field, but it does. So you have to keep open mind about Smackover. There's a lot of room for structural stratigraphic traps. Most structures are built. I just showed you this. You want a large, well-sealed structure closure, or you want several oolite lobes terminating a major Smackover Buckner Formation cycle boundary. That's going to be Walker Creek. Or you want to have a deeper basal upper Smackover microbial reef facies that contains a shallower pool and Smackover oolites. That's Little Cedar Creek and probably Midway Field. Number 5, you must be in an area where an active old generation center exists that contains good to lower Smackover Formation source rocks. That's J Formation Field. You must be in an area where a large hydrocarbon trap was formed before during the lower Smackover source rock expulsion phase and never breached. That's a lot of fields. You must be in an area where Smackover reservoirs are not so deep that evaporite-associated thermochemical sulfate reduction has destroyed Smackover reservoir system in the hydrocarbon trap. So what it tells you is, if you're going to 16,000 feet, you're not looking for oil and gas. You're not looking for money. You're just looking for oil and gas. Finally, it helps be an area where you have basement vault wrenching, enhancing trap closure. That's Bryant's Mill and Midway Field. I think that might be the last slide. Oh, no, one more. Look at where we are right now. What happens when you drop oil prices? What plays no longer work? You don't have to worry about the carbonate plays. They're in shallow water on shore. Shale gas, it's toast. Bakken becomes very much of a problem between $65 to $70 a barrel. Jack and St. Malo below 60, it's toast. Look at all these other fields in right here. Get down to 50, man, half of your fields and plays you make, they're gone. Get down to 40, some serious problems right here. When you come back down to Toronto, it's actually a carbon field. These devastating decline be down here. We hope that never happens. And that's all I have to say. I'm open to questions. By the way, I don't totally understand the Smackover. I'm still learning. I've been studying for 5 years. I'm still learning. But I've been beating on it pretty hard. Yes?
What basement events and the separation from Africa do you think is represented by the state line time?
Well, you're getting pretty close to that the shear that runs off South Florida shear. But the trend that it comes off of is one of the old Eagleford horse blocks, what it is. And it got rejuvenated. It possibly could have got rejuvenated because it sits right along that South Florida shear. But that rejuvenation made a lot of oil fields that wouldn't have existed normally. Any other questions? Yeah.
What technology would you recommend to look for new traps in the Smackover? Do you have to have 3D or do you have to have additional?
Well, you start out with 2D and you work out the cycle boundaries and where you think for the right place to work the cycle boundary is. Because mostly what you're playing now is strap trap. Let's get rid of it. If you're playing something other than strap, then you're playing a trap on the side of a major anticline. You've got several of those still left. And people have tried to drill, but they've come along strapping and it didn't work. They just didn't go down dip. But what you have to do is work it out, see the strategic logs. And quite frankly, if I would go to the 2D stage at that point in time, see if you can work it out 2D. But really to work Smackover, you really want 3D seismic, you want higher resolution 3D. I didn't go into that because that's about another 30 minutes of talk. I'm amazed all you people stayed this long. But the second part of my slideshow, about a third of that is how you do it seismic. Part of the problem with Smackover is the oolite zone at the top. By the time you bear it down to 10,000 feet and you have those high velocities, it's hard to actually, it's too thin time-wise to be able to resolve. So you never know if you're seeing some kind of aberration due to a side lobe or actually not velocity. I've got a slide in there somewhere which shows a line coming off the, just east of Chalmette Springs field. You see all these real steep foreset beds, and guess what? They're carbon. And you look at the line on the other side, first of all, I wonder why upper degradation began there. That's Smackover, or the Buckner. Aha. That line is, at the state line, it was 3D where all the oolite lobes were. North of that, it was all 2D. You could still see the cycle boundary. You couldn't see the individual Smackover lobes. So a lot of it really is you have to get the high frequency seismic. You try to do low frequency seismic, the kind of problems you have, difficult. Any other questions? Yeah.
Steve, two-part question about the drawbridge structures. One, do you think there are very many untested drawbridge structures out there? And two, do you think the proximity of the sea level against salt reduces the heat load by salt wicking away the heat, as some folks support, providing you with a possibility for a higher probability of oil as opposed to gas?
On the second part, I'd say yeah, it probably would. You get a better chance of getting a little bit of it really kind of depends on what's going down dip, because up against that salt structure, you're feeding it with some low down dip. It's probably 800,000 foot down dip. So whatever that generation stage is down there is what you'll be getting up to. You may have an oil cap, a gas cap to an oil run around it. Secondarily, yes, there's still some drawbridge structure kind of traps out there. I saw some in the East Texas Basin when I was cruising it. But here again, you're going to have to, number one, a lot of these places you need to look for that already have fields in the woodbine above it, or in the Biloxi sandstone, so then you have a problem trying to get somebody daisy chained in there to farm out their acres to be able to shoot the field. But yes, I think they still exist, yes.
Since you're still talking to me, third part, any knowledge at this point of any attempted horizontal completions in the ground depths?
I would think they'd be problematic, personally. Anytime you try to frack carbon, it's a good problem. If the whole thing, if the brown dense is there, then you got no reservoir top that, you may be okay as long as you've got Buckner on top of it. But if you try to fracture a frac, the brown dense, you got oolites right above it, well, guess what? It's toast. So I thought of that for about 10 years ago. I basically decided that, well, you can't do that, and you get all the problems with H2S in some areas, yada, yada, yada. Figure that, not my lifespan.
I'm doing pretty good if I within 10 years of you. Great song. Thank you so much.
Thank you. Any other questions?
In the Shuaibah, in some of the fields in the Emirates, you see zones of intense stylization right near the edge of the porosity in the Shuaibah, where there's been very early oil infill preserving the porosity, and I wondered if you'd ever encountered anything like that in the Smackover.
Well, Smackover has stylites, and some of the stylites have oil in them. By the way, the Shuaibah formation she's talking about is Slider. If you want to translate that in the Gulf of Mexico, that's Slider Formation. And there's a big field. In fact, the second part of my slideshow that I never showed it because I didn't want to make this 2-hour talk. You've got a 772 square mile 3D over the platform, with the shelf margin, and into the prorated oolite lobes that Sharon wrote an excellent paper. I was stunned that they wrote it, number one. I was stunned they wrote it. I was stunned they released it. That giant hydrocarbon petroleum reservoirs of the world. And it tells you how they handle all these complex environments. They're using co-rendering seismic attributes. And what they're doing now is they're coming into this snorkel. They can actually take these attribute-like lobes, which is what? That's the pattern. And they're imaging the lobes. And what they're doing, they're drilling down there, projecting, subtracting, and taking out oil up there. And they're doing this all in 3D, and they're making good money doing it. So there's a potential still to do that. Nobody's done that yet. There's all kinds of potential in carbons. People just don't understand. I mean, what's the Buckner Formation? Sandy dolomite. What's the Wolfberg? Wolfberg is carbon debris plays in the Permian. Not too dissimilar to what you have over there in the Poser Rica field. That'll ultimately produce about 2 billion barrels. But everyone wants to play the sandbox. Nobody wants to snorkel around the reef. Personally, I'm old enough where I still like to snorkel around the reef. You got a question?
Steve, that was an excellent talk. And here is a brief, small award to thank you for giving it.
Thank you.